Welcome to another episode of Quintus Technologies Tech Talk. I'm Chad Beamer, Application Engineering Manager with Quintus Technologies located here in Columbus, Ohio. As many of you know, we work very closely with universities here in the U.S., reaching from the East Coast to the West Coast. Today, we have two individuals based out of the West Coast representing the University of Washington. So let's jump right into it. Dwayne, Rick, can you introduce yourself and highlight some of the collaborative-based projects you're spearheading at the university?
Sure. Good morning, Chad. Pleasure to be here with you. I'm Dwayne Arola. I'm a faculty member, professor in material science and engineering with an adjunct appointment in mechanical engineering.
Yeah, thanks for having us today, Chad. My name is Rick Schleusener. I am a PhD student in the material science and engineering department at UW, and looking forward to giving this tech talk today.
Chad, you asked if we would share a little bit about the things that we're doing here at the university. Before I do that, what I'd like to do is just talk a little bit about the University of Washington in Seattle. You know, whenever I get a chance to share with people, I like to talk a little bit about the recognitions. And so with regards to the university, we're actually ranked number 8 amongst best universities in the world. And if you limit that now to universities within the United States, we're ranked as number 2. That's an evaluation that was conducted by the U.S. News and World Report. We're also number 1 in most innovative public universities in the world, an evaluation that was performed by Reuters. And turns out that maybe because a lot of the industries in this area that we have more graduates from the UW in the world's largest tech companies than any other U.S. university. So we're very proud of those things. With regards to the work that we're doing with other companies, so we're very lucky. In material science, we have efforts that are focused on all aspects of the materials tetrahedron. And then also with regards to materials, I'd say that we have all materials represented. We have efforts that are focused on biomaterials, in battery materials, in quantum materials, in sustainable materials, in AI applied to the development of new materials, and then also, of course, structural materials. Process relationships, which is my primary area, and the focus of the team that I lead. So with regards to our efforts, we have activities, collaborative activities actually, that span in laser powder bed fusion, focused on the point from the location where powder enters the machine, focused on powder oxidation, and then also the development of condensate, how that causes aging of powder, on inert gas flow, the distribution of inert gas flow within the machine and how that influences on protection of the melt pool and other aspects of build quality. A lot of focus on property variability, which I hope that we'll get a chance to talk about today. Property variability that results from processing variability. And then also at the end, we have efforts focused on surface treatment, post-processing to be able to improve surface texture and surface integrity.
So, I mean, it's impressive. Obviously, you're contributing to this success that University of Washington is having, and very broad technical aspects that you're working on that are near and close to the various industries we work with. Process variability, all right, in laser powder bed fusion. That is a significant topic here at Quintus Technologies, and it impacts a number of industries we support, from aerospace to space and medical, to name a few. Can you highlight this work in more detail, as I believe it's going to be of significant interest to the companies and organizations we directly work with?
Yeah, I'd love to. It turns out because of the large aerospace footprint that we have here in the Pacific Northwest, we get to watch the growth in the use of laser powder bed fusion, and the conversations about pain points come up. And one of the pain points is process variability. So as people are looking at industrialization now, and not so much focused on just fundamental research, but trying to understand how best to be able to apply the processes to be able to producing production parts, the question is what sources of variability there are that contribute to property variability, and how to be able to mitigate them. And so with regards to process variability in laser powder bed fusion, it can be with regards to any metal, but we're largely focused on titanium, the workhorse of the aerospace industry. There's 3 components. So those 3 components that we refer to are intra-build variability, and that refers to the variation in properties that we might find for metal that's distributed across the build space of a single machine. Inter-build variability, which is if we need to be able to produce parts in multiple builds, what are the differences in the part quality and the part properties we might find still using a single machine. And if the demand for the parts and the production is high enough, we'll have to recruit multiple machines. And then we're worried about inter-machine variability. And that refers to the fact that each machine can be operated slightly differently, even though it might be the exact same model and perhaps even utilizing the same powder. So we're concerned about what aspects of variability are present in the properties of the metal and what components of process physics contribute to that. Those three components of variability all...
And Dwayne, this is critical when you're looking to scale additives,
That's
right? We're starting to see a transition in a lot of industries we serve where it goes beyond just one printer, potentially farms of printers, right. And that's where the challenges with process variability are magnified, I would assume.
Exactly, yeah. All three of those components of variability contribute to the reliability of components, and so it's key to be able to understand each one separately and then understand how they're contributing to bottom line. So if we get a chance to talk about the nuts and bolts of our program, the way that we're actually trying to address variability in laser powder bed fusion, again focused on titanium, is utilizing a round-robin program. So we've been operating a round-robin program here at the University of Washington for about the last 3.5, 4 years. And the way that we do that is we tackle these three components of variability through, one, build design, by actually incorporating a build design that allows us to be able to spatially distribute metal across the build envelope and allows us to be able to then characterize properties according to the range in space, as well as the potential influences, things like gas flow, and then also recoater blade movement. We perform multiple builds of the same design in order to be able to tackle the inter-build variability. And then with regards to the round-robin program, the key is that we've been able to find partners which are very interested in this aspect of production. And so what they've done is they've joined us as a team. So our round-robin program has approximately 6 members, all operating the same machines, all utilizing the same powder. And what we're doing then is evaluating the variability in the metal that comes from those three components, inter-build as well as inter-machine contributions.
Yeah, and Chad, if I could jump in here and give you a bit of a description on some of the work that we're doing, I'd love to share some of our data with you. So the first sort of point of when we get our metal fresh off the printer, the first thing we need to do is put it through heat treatment. And so a standard...
So you actually have to heat treat the material, is that correct?
That's correct. So at minimum, stress relief heat treatment is required for laser powder bed fusion machines. So that is applied to a portion of our metal in our study that we're currently performing, but the majority of the metal is actually subjected to a low temperature, high pressure HIP cycle, courtesy of Quintus Technologies. And so you can see on the screen here, I have 3 plots that are showing EBSD band contrast images that show the relative grain sizes for each of these heat treatment conditions that we have. And you can see that the HIP process is actually coarsening our grains, which is beneficial overall. And then also when we look at our internal microstructure through micro CT, this is perhaps the most beneficial factor for the HIP process in laser powder bed fusion. You notice that in the stress relief state, there are numerous voids and internal anomalies that are present. But after we hit the metal and we double check using micro CT again, you can see that these voids are almost effectively eliminated entirely due to the heat treatment. This is very beneficial, especially in fatigue applications. And I'll highlight some of the initial fatigue results that we have. So I'm showing 2 kernel density estimate plots, essentially histograms showing the distribution in cycles to failure for our stress relief metal versus our HIP metal. And we've also separated the data based on specimen orientation, both vertical and horizontally oriented metal. And so the first thing that jumps out at me when we compare the hip and the stress relief metal is, first of all, the hip metal is actually increasing our fatigue life, increasing our number of cycles to failure, which is great to see overall. And then the next thing, interestingly, is if you compare the differences between the vertical and horizontal conditions, the hip process is actually reducing the differences in the fatigue performance between those two specimen orientations. So also another very beneficial result of the hip process itself.
Kind of helps homogenize, right, the material and get kind of a uniform behavior in various orientations, correct?
Yeah, exactly. And then I also wanted to highlight some interesting findings that we have in terms of our intra-build variability. If you recall, Professor Arola described that we split our build space up into multiple zones, and we wanted to see if the fatigue response was any different in any one region of the machine versus another. So in our initial testing for the stress relief case, we noticed that our zones 1 and 4, those farthest from the operator in the back of the machine, are actually lagging behind a little bit in terms of fatigue performance. And I've shown various fractographs on this slide here. So you can see kind of the extent of some of the defects we're looking at, some of the root cause failure origins that we see, a lot of lack of fusion in these zones 1 and 4. So with these zones lagging behind, however, in the stress relief condition, if we turn around and look at the metal in the hip condition, we can see very good agreement across all 5 of these zones, which effectively, the hip process is effectively reducing our differences, not only between specimen orientations, but between the printing regions, the location that it's printed in on the build plate, which is great to see.
Yeah, you don't want to have to design a part based on location on the build plate, right? You want to be able to assume similar properties across the entire cross section, I would assume.
Yeah, exactly. Design for additive manufacturing is supposed to make things easier, not more complicated, I think. Yeah. But yeah, on this slide, I'm showing some of the root cause failure origins from fractography as well. And you can notice that there are no lack of fusion voids that are present. We have a lot of carbon FOD as well as some tungsten FOD failure origins that I'm showing here. So leading to our next sort of summary slide here is that in the stress relief condition, we saw that failure was dominated largely by porous anomalies. And we did observe some FOD failures, but there were some extensive differences between zones and orientation, et cetera. But in the hip condition, one thing we noticed that there were 0 porosity-related defects observed on our fracture surfaces. So kind of confirms what we saw in micro CT. And it allows us to kind of see more of problems in our microstructure. There's a lot more of these FOD failures that are arising because there are a lack of fusion voids present in the metal. So the hip process has really allowed us to learn more about what's going on in our metal as well.
So what we're seeing is this lower temperature, higher pressure hip strategy, AMS 7028, for those who are unfamiliar, was extremely effective in eliminating a failure mechanism. And in turn, you get improvement in your predictive properties and resulting design allowables for critical components that are used in the aerospace or medical industry, I would assume.
Yeah, I think you hit the nail on the head. That's a great summary of what we've observed from the hip process so far.
And I mean, this is a great data set because we've seen snapshots of these type of data sets behind the scenes, but often owned by private companies and can't share them to the additive community. So I think this is a very impressive effort here. It captures, what I love about it is it captures a process, structure, property relationships that we like to seek out, with the addition of some intense fractography. And I think that's extremely important when you're dissecting this kind of data. So I got a couple questions for both you, Rick, and Dwayne. Question number one. This work was performed on a workhorse alloy, a Ti6Al4V, which is used heavily in a number of industries, aerospace and medical included. Some of these results that we see here, would we assume similar results for laser powder bed fusion of nickel base, copper base, and even aluminum base alloys?
Yeah, great question, Chad. The answer is exactly yes. The reason is because as long as we're able to perform the same reduction in the size of those lack of fusion voids, we would expect to see the same relative improvements and homogenization of metal, both within the machine as well as across partners. So that's actually something that we're hoping to get involved with.
Excellent. Which is kind of a great lead-in. I mentioned you're going to be presenting at ICAM in a couple months, beginning of October, and doing even a deeper dive on this body of work. So that's extremely exciting. But what's next for this project?
Yeah, we're excited about ICAM, so hopefully we'll be able to spend some time there together. With regards to the program, I think there's three aspects that we're going to be continuing with. The first is growing the data set. The reason is we've had people reach out to us that want to get involved, include their machine in the effort. We found that a lot of companies can utilize this data as a source of qualification for their machines. Understanding the variability that they might be having on their own machines, and if, for example, the hip treatment is working just as well for them. The second thing that's important is that we're finding, because of the advantages of hip, that this other underlying aspect of range of defects, the foreign object debris, is interesting, and we want to start to examine different feedstocks to distinguish if we find the same kinds of problems with a range of feedstocks. And then lastly, if this is a universal problem, how are we going to be able to identify it during builds or prior to that? So we're working on trying to distinguish in situ techniques to be able to identify these sources of anomalies and their contribution to fatigue response.
So it sounds like there's some very interesting work that lies ahead. And it sounds like you're open for further collaboration. So that's excellent. For me, it's been a pleasure working with you. I think our relationship maybe dates back a couple of years.
At least.
Back to Powder Met AMPM. Rick, I believe I met you face to face out in Portland a handful of years ago, 3 or 4 years ago. We value this partnership. It's great work that you're doing. And I thank you so much for sharing it with the additive community.
Yeah, thanks for the kind words, and thank you for always being supportive of our efforts. It is a really great partnership that we have.
I'd just like to close by saying that I'm extremely appreciative to a large number of individuals and organizations who have made this work possible. I think that we've learned a lot along the way, and it's been a result of the large team that's been contributing to the work that we've just been able to describe, and that also we'll be covering at ICAM. So thank you very much.
Excited, looking forward to that. Once again, Dwayne and Rick, greatly appreciate your time and the desire for collaboration on this front.
Excellent. Thank you. We're looking forward to it as well.
Thank you, Chad.
Thank you.